So, good afternoon, everyone. Hope you all are doing good. So, let's get started with today's session. So, we are at week 5 right now. So, moving on to the first question. So, this is the first question that we are going to solve today. Okay, so the question is, in this particular circuit, we have to find out the value of Wn. So here we can see there are several WPs and WNs showing that these are PMOSes and the bottom ones are NMOSes. So here it is given that R is 3.7679 kilo ohms, WP is actually 4 times Wn, mu n Cx by 2 is 3.15 millisiemens per volt, and mu p Cox by 2 is 0.788 millisiemens per volt. Given that Vtn is equal to Vtp is equal to 0.3 volts, and assuming Ln equal to Lp equal to 1 micrometer. Okay, so can you please let me know why do we have this condition of Wp being 4 times Wn, this particular condition? What is your take on this particular condition, like why this condition has been given?
To make symmetrical, ma'am, PMOS and NMOS.
Yeah, to make them symmetrical, basically we want IDN is equal to IDP. So for ID, we know that in these type of circuits, our MOSFET, when we are trying to design an amplifier, our MOSFETs are in saturation condition, right? They are in saturation region. So the current equation will be mu n Cox by 2 VGS minus VT whole square. This is the basic formula that we'll use. So since here we can observe that these transistors are in series, all these transistors are in series, right? So same current should flow through this circuit. So here if we clearly see, let's say considering this left side, so in this left side all the transistors are in series and there is only a single current path. Like, let me show it to you clearly. So here let's say a current I is flowing, okay? So this current will flow here. So will there be a chance that we see a current in this direction? Is there a possibility?
No, ma'am.
No, right?
No.
Because this is a gate terminal, so there won't be any current in this direction. Now moving ahead, the same current will flow through this NMOS. Now again here this divergence appears. So do we see any current? No, because this is similar, right? This is also like this is also connected to gate terminal, so there won't be any current. So this current again moves forward, and this is the same current which will go through the resistor. Here again there is this diversion, but current won't be going through it because it is connected to gate. And similarly here, so we observe that from VDD to ground, this is ground, right? These two are ground terminals. So we see that from VDD to ground there is only one current path. So a single current can flow through this particular path. That means all the current in each of these particular devices will be equal. So both the PMOSes are matched, both NMOSes are matched. What do I mean by matched? That means they both have same values for mu and Cox and for W and L, for PMOS as well as NMOS. Now coming to PMOS and NMOS, So is there a possibility that PMOS and NMOS can be matched? So let's say by matched I mean is there a possibility that we can make equal physical sizes for NMOS and PMOS and we can get equal current? Is there a possibility? By making the physical parameters equal for PMOS and NMOS, is there a possibility that we can get equal currents for NMOS and PMOS? Is my question clear what I'm trying to ask? So basically what I'm trying to say is, let's say
I think no, ma'am,
no, okay, can you,
because mobility of holes is less than mobility of electrons.
yes, you're right. So let's say if I make Wn equal to Wp, Ln equal to Lp, so in our current equation we have mu n Cox W by L, right? So these parameters we have matched, but when it comes to Cox also we can match because it depends on our dielectric and its thickness, so we can match Cox. But where it creates an issue is this mu n, because mu n of is like greater, it's greater than mu p. So that is the reason it is not possible in a normal CMOS technology to design PMOS and NMOS with same physical parameters providing us same currents. So that's why we are going for different sizing so that we can match IDN equal to IDP. So here it is clear like why there is a single current and why it need to be matched and how we are matching, that is also clear in this question, right? Does anyone have any doubt in this particular thing? So why there is only single current flowing through? So there are few questions, like question number 1, why single current? Is this clear? Why there is only one current flowing through this branch? Hello?
Because all are in series and gate current is 0.
Yeah, so that this question is clear. Next thing, okay, so why can't we have Wn equal to Wp and Ln equal to Lp, but also IDN equal to IDP? This is also clear, right? Why we can't have this particular thing? Why this condition is not possible? This is also clear. That is what we discussed, right? That is because mu n is greater than mu p. This question is also clear to us, right? Now since we want our currents, so here since single current should flow, IDN equal to, that means IDN equal to IDP, and how this IDN and IDP are matched in this particular question, that is also clear to us, right? So here we have separately sized the NMOS and PMOS such that we get these conditions. This is also clear to us, right? Hope this is clear. So let's move ahead. If you feel any doubts or if you have any concerns, please let me know. Okay, you can maybe raise your hands or just unmute yourself and ask. I'm fine with that. Okay, so yeah, okay. So in this question, we have to find out the value for Wn, right? It is given that ID is 153 microamperes. So ID, this is IDN, is equal to IDP is equal to 153 microamps. This is also given. We want our mu n Cox by 2 VGS minus VT, mu n Cox W by L, right? Wn by Ln, and here it is Wp by Lp. So these need to be matched. So the moment we go for Wn by Ln, it becomes 3.15 Wn, this is actually equal to 0.788 into 4, which is mu p Cox Wp by Lp. So these two are actually equal. So that means we can cancel these two out. Now we are left with VGSN minus VT whole square is equal to VSG minus VT whole square. Square will be, let's cancel. And we know VTN is equal to VTP. So that means these two will also be cancelled. So that means VGSN is equal to VSGP. This is clear to everyone? Is this clear to everyone? How we got VGSN equal to VSGP? Any doubts in this particular in this particular solution? How we got this? This is clear, no? We simply equated the currents and we simply nullified all the we simply removed all the equal parts, and then we came to this conclusion that VGSN is equal to VSGP. This is clear, right? So now okay, now what we have to find out? So we need to
Why
find,
did you cancel that
sorry,
mu n and mu p, ma'am?
yes, so that is what I was saying. So here it is given mu n Cox by 2 to be 3.15, right? And UP Cox by 2 is 0.788. Okay, in our formula we have mu n Cox by 2 into W by L. Okay, so when we put this W by, so let's say Wn by Ln remains as it is. When we are going to Wp by Lp, rather than Wp by Lp, what I'll do, I'll put 4 times of Wn, because Wp is 4 times of Wn. Okay, and when we do this calculation, so basically 0.788 into 4 is 3.15. You can do it and check. So this makes them, basically makes these two constants equal. That particular condition makes these two constants equal. And also
Okay, ma'am.
VTP and VTN are equal. So we have also removed those. So ultimately we came to this conclusion. Clear?
Yes, ma'am.
Yeah, okay. So let's move ahead. So here we have got this thing. Now what is asked? So we want to find Wn. Okay, so what else we can figure out from this particular image, right? So looking at this left side circuit only, let's concentrate on this left side circuit. So if we clearly observe this circuit, so if I say the 2.5 volts is getting dropped across this particular circuit, which is between 2.5 volts to ground. This is clear, right? So if I say my 2.5 volts is getting dropped, so across what all points it is getting dropped, so 2.5 volts is actually VSD. Let's say this is transistor 1, 2, 3 and 4. Okay, so VSD1 plus VSD2 plus I across R, so IR, I'll directly write IR. So this current and so drop across this resistor, then VDS3 and VDS4. This is clear to us?
Yes.
This is clear, no?
Yes, ma'am.
Here we know VD equal to VG. Since this is a diode configuration where VD and VG are shorted, like D and G are shorted in all the transistors, you can observe. So this is a PMOS. So here we have source drain, In case of NMOS, this is the drain, this is source, this is drain, and this is source. So we can see that VD equal to VG. So that means VSDN is equal to VSGP and VDSN equal to VGSP. So VGSN. So VSD will be equal to VSG and VDS will be equal to VGS. This is clear, no? So this will become 2.5 equal to VSG1 plus VSG2 plus IN2R plus VGS3 plus VGS4. Okay, so we came across this. This is finally what we got. Okay, so this is finally what we got. Now moving ahead, so we also found this expression, right? This one. So here VGSN is equal to VSGP. So let's put them in single terms. So let me I'll make all of them as VGS. So it becomes 2.5 equal to VGS into 4 plus IR. This is clear, no? Now we know I is ID basically. So ID is NCox by 2 Wn by Ln VGS minus VT whole square. So it is ID by NCox by 2 Wn by Ln root of plus VT equal to VGS. So in place of VGS, basically we'll substitute this. So we'll get 2.5 equal to 4 times of root over ID by mu n Cox by 2 Wn by Ln plus Vt plus ID into R. We know the value of R. ID we know. ID is 153 micro. R is 3.79 kilo ohms. Mu n Cox by 2 is 3.15 millisiemens per volt and Vt is 0.3 volts. What else? Ln is 1 micrometer. Wn remains Wn because this is what we need to find out. So after substituting these values into this particular equation, we are only left with Wn as the variable. So we have to find the value for Wn. So basically we have to solve this expression, solve this particular equation, and we'll find the Wn. So would you like to try this out? Maybe you can try this out later. I'll quickly let you know the answer. You people can solve this and cross check. So it is 1.5 micrometers. So Wn is 1.5 micrometers. Is this clear? Are these steps clear? Like how we proceeded one after the another from the given
Yes, ma'am.
particular information? This is clear, right? So you can simply
Yes.
solve this final equation by substituting these values into them and you'll find this value. Clear? Okay, so yeah, so let's move ahead and let's move on to the next question. So in this particular question, it is given that lambda is 0.1 per volt. So what do you think, why the lambda has been given? Why there is this lambda being introduced in this particular question? It was not mentioned earlier. So it will basically give rise to R naught or GDS. Okay. So when we see this type of circuit, this particular circuit, in this type of circuits, when there is R naught, okay, so when we have this type of circuit, this particular circuit, so in this case, now we have to find out what is the small signal gain. So in general, when we talk about small signal gain or gain, in very general, it is actually GM into Z out. In general, gain is transconductance into output resistance. Okay. Does anyone have any doubt in this case? So gain in general is actually transconductance into Z out, your output resistance. Transconductance will come from your input transistor, the transistor in which you are giving input to, and output resistance is basically the resistance seen from the output node, that is from this node, whatever you see, the resultant resistance will be your Z out. So the gain is GM into Z naught. Okay. So in this particular configuration that we are seeing in this particular image or in this particular circuit, the Z out turns out to be 2GD plus GM by GD square, or in terms of R naught, it becomes GM R naught square plus 2 by R naught. No, sorry, 2 R naught. Yes. So it becomes this, and this is for like when there are two transistors. Okay. So like if there are two transistors, you are seeing output from here and you are giving input from here. So for this particular circuit, your Z out becomes this. Okay. So now what is different in this particular circuit and the circuit that we are seeing? So we have two PMOSs also, right? After like on the top of this output point, we have two PMOSs connected, PMOS circuit. So it will also provide some resistance into the circuit now, and this will be so simply if I say GDN, GMN, GDN. So this is for NMOS circuit. So for PMOS circuit, it will be simply N will be replaced by P. So GMP by GDP, or GM R naught P square NP to R naught P. Okay. So what will be Z out total? Yes, what will be the Z out total? If this is the resistance.
Parallel.
Yes, these two will be in parallel, because one is at the top, other is at the bottom, and we want it at this particular point. So they become parallel. So it will be Z out NMOS parallel Z out PMOS. So which will basically give you the value GM R naught plus 2 R naught by 2. In this particular case, GMN equal to GMP, it's already mentioned in the question, and R naught N is equal to R naught P. So hence there is no bifurcation between GMs like GMs and R naught. So we can simply remove all the N's and P's and we can write this way. So this is the Z out total, and GM remains GM. So gain becomes GM into GM R naught plus 2 R naught by 2, and we'll have negative. Why negative? Yes, in this particular circuit the gain will be negative. Why negative?
Because the MOSFET to which the input is applied is in common source mode.
So basically you want to say this particular circuit is in common source configuration. How? Because the input is gate, output is drain terminal. So this configuration is CS configuration, right? And we know the gain in CS configuration is out of phase. That is, there is a shift of 180 degrees, or in general we can say the gain has negative. So that's why we'll introduce a negative. Okay. So you can substitute the values in this particular formula and you can try. I'll let you know the value that you will get for gain. It is basically minus 6232.042. This is the value that you will get for gain. Okay, you can try and check whether you are getting this particular answer or not by substituting the values in the this particular formula.
Hello.
Yes.
Ma'am, when you calculate Z out,
Yes.
then there will be Z impedance corresponding to left side branch also, isn't it?
Okay, so you are saying the impedance corresponding to this particular branch?
Left circuit, yes.
Acha. So let's look into this particular point. So if I am taking this particular point, can you see this particular point?
Yes.
So in this particular point, it is connected to gate, right?
Yes.
So at this point, and gate, so here it is basically open, right? So you will not see the impact of this that particular circuit that much. Also, when I say, so basically how do you find out a drop or how do you find out an impedance at particular point? So let's say these are my transistors. You want to find Z out at this particular point, okay? So what you will do, you will basically apply a voltage source. There will be a current flowing, and Z out will basically be equal to
Vx by Ix.
yeah, Vx by Ix, right?
Yes.
So when you're saying Vx by Ix, so that means it is the current that is flowing through this particular circuit and this voltage, the ratio. So usme when you'll see here, this Vx will come across this these two transistors as VDS, and this current will come across these as IDs, right? So यहाँ
Yes.
पे at this particular point, what is connected, it makes very less sense, but I mean you can solve this out like how should I solve it? I don't. So How do you solve it? So basically you apply current here, right? And there won't be any current in this particular branch. So the same current will flow from here and the same will continue till this. So इस particular branch में इधर जो connect हो रहा है this diode configuration, उसका you are not seeing any impact, right? In this current's behavior.
Yes, and current in that branch is also 0. So
Yeah, current in this branch is also 0.
And for AC analysis, this node will
Sorry,
be
okay.
you are not audible.
not audible. Still not audible.
Yeah, you are not audible.
Just a second.
Hello?
Yeah, am I audible now?
Yes, yes. Go ahead.
Yeah, so I am saying for AC analysis, this node will be grounded because this is DC, right? For
Yeah,
we are for
yes.
bias.
And in that sense also you can see. So here this is your AC node because input is here. Okay? So this node will be your AC node. This particular node will be AC node. Now coming to this node. So will this node be an AC or DC? So this node, then this is AC. That makes this AC. This is AC. What about this particular node? Will it become a DC node? Hmm. This is AC and this is AC. It is clear. This is AC node. What do you think? Will this become a AC node or DC node? This particular
I,
node.
yeah, I think for AC analysis that will be AC ground means since it is a DC, it will be grounded.
How can you say that this is a DC?
Because input we are applying at first MOSFET gate
Yes.
AC input and
Right.
all other nodes are for DC biasing. So when we will do AC analysis, all will be grounded except this uh, where input is applied, AC input is applied.
Hmm. Actually, these are for constant current biasing. Constant biasing के लिए ही होता है ऐसा तो नहीं है. Maybe you can say it that way, but no, why I'm asking is, so let's say at this particular point where we are applying AC as input, so here we have AC, right? So since this point is as AC, so this point is shorted to this particular point also on the left side of circuit, right? So that
Yes,
point will also become AC. And when that point becomes AC,
but we have used a high resistance there, right? So this resistance is of high value, so very small current will go to that path.
high resistance. Which path are you saying that will be a high
So
resistance path?
we have
Okay,
one
so this R
resistance.
you're saying.
Yeah. Yes.
So this was how
Ma'am,
much?
in lecture, sir said that that resistor actually isolate two circuits.
Okay, this particular resistor, this is
Yes.
3.9 kilo ohms, right?
No, this register value is not given, I guess.
This is not given.
Yeah.
Which R was given? One R was given, no? R is 3.79. Okay. So this one is not given, no?
Yeah.
Okay. So yeah. Acha, so since this being very high resistance, so if this is very high, that means at this particular path there won't be much current flow. So this point will actually behave somewhat as DC. So if that's the case, then this point will definitely become a DC. Right, makes sense. And this will become AC. So if this becomes DC, then तो ये AC short हो जाएगा, AC ground हो जाएगा. तो इस particular diode configuration का there won't be any impact in the resistance. Yeah, makes sense. Right. So sorry for the disturbance. So we were discussing something. The class. I would like to know if you want to understand what we were basically discussing, or is it fine? So you people are not confused, right? Or do you want me to repeat what basically we were discussing right now for last 5-10 minutes? So I'll
No,
quickly.
fine, ma'am.
It's fine, no?
Can we move to next because
Yeah.
very less
We
time
can
is
move.
left.
Oh yes, it's very less time is left. So basically the conclusion is that this point is also DC. So this particular node, this particular node is DC. That is because this resistance over here is actually very high resistance, which will separate this left side circuit. So making this circuit almost like almost insensitive to the AC input signal. So that's why this point will become DC. So these left side circuits impedance will not come into picture for our Z out. So that is the basic conclusion that we drew. Okay, so moving ahead. Yeah, so this particular question. Now coming to this particular question. So in this question, what is given? Like
Ma'am, question 3 is left.
question 3. Oh, okay, I have picked few random questions with different flavors. So
Okay, ma'am.
I must have left that
No issue.
question. Yeah, I came to this particular question. Maybe I'll, if time permits, I must have kept it at the end or something. I'll discuss it. So yeah, so in this particular question, it has been given that VTN and VTPs are equal to 0.3 volts, and mu and Cox mu and Cox by 2 Wn by Ln, and mu p Cox by 2 Wp by Lp. This has already been taken care of. Okay, so here Wp and Wn are such that these conditions actually satisfy. So iska tension lene ka we don't need to take care of this particular thing. So now what they are saying, like what will be this current I across this resistor, that we have to find out. Okay, so let's quickly analyze this particular circuit. So here, since this condition is satisfied, VTP and VTNs are satisfied, and this particular configuration, so this particular circuit part is in series, so same current I will flow through this particular circuit, right? This is clear to us? Is this clear?
Yes.
Yes.
So since that same current is flowing, so there will be certain amount of voltage that will be generated at these 2 points, right? These values will be replicated at these points, so which are basically gate terminals. We know for ID we have mu n Cox by 2 Wn by Ln Vgs minus Vt whole square. This is the formula. So in our formula we see that we only have the impact of VGS, right? So here in this particular transistor and in this particular transistor, the VGS is same. Can you see that? Similarly, in these two transistors also, VSG is same. Sorry, here VSG and here VGS, same. This is clear, no? Because gates are shorted.
Yes.
So, in this particular transistor, let's say this I is flowing, no? Here I is flowing. So, in this particular transistor also, I will flow. This is clear? Because in this, like for NMOSes I am talking, okay? For NMOSes, Wn is equal to Wn1 equal to Wn2, Ln1 equal to Ln2, mu n Cox by 2 is equal for both. So since everything is equal, and with this we have VGS1 equal to VGS2, VT1 equal to VT2. So these transistors being 1 and 2. So since all these are equal, so they will have same currents. So the I1 or small I1, let's say small I1 will be small I2. This is clear? Yes, I1 equal to,
Yes, ma'am.
how the VGS is turned on?
sorry.
How the MOSFET is turned on?
So MOSFET is already turned on, and in this particular circuit, they are also in saturation. How? Here you see VGS equal to VDS, okay? And we know VDS should be greater than or equal to VGS minus VT, and this condition will always be satisfied. So these two MOSFETs, these two MOSFETs, A and B, A and B are always in saturation, right? This is clear?
We are assuming it, or
No,
is
see,
it?
in
Okay.
both these conditions, this is gate terminal, this is drain, right?
Yes.
So VG is equal to VD for both the transistors. That means VGS is equal to VDS, like for PMOS or NMOS we
Yeah.
are
Yeah.
considering. So this is equal. For
Yes.
saturation, what we want, our
Yeah.
VDS
VDS is
should be
greater
greater
than
than
VGS.
equal to
Yeah.
VGS minus VT,
VT.
right?
Yes.
So
Yes.
since these two are equal, that means this is always less than VDS.
Yeah. Yeah. Got it. Okay.
So they are always in saturation, right?
Mm.
Right. So these two are always in saturation. That is clear. Now, how we got I1 equal to I2? Is this clear? Like how the current through these two NMOSes is equal. Is this clear to everyone? That is because all
Yes,
these
ma'am.
parameters are equal for these transistors, right? So I1 is equal to I2. That is clear. Now what about, let's say this is 3. PMOS is 3. So what about this PMOS? What will be the current across that? So if we see for this transistor, let it be 3, let it be 4, okay? So for first PMOS, we had WP. This is P dash is actually 21 times of WP. This is for P4, okay? LP3 is equal to LP4. Length of both the transistors is equal. Width is 21 times, okay? VSG3 is equal to VSG4. This is also equal because they are shorted. So VSG will be same. Now when we have this thing, and mu and mu p Cox by 2 will always remain same. So what does this show? This basically shows that I4 will actually be 21 times of I3. Is this clear? Why
Yes,
we
ma'am.
got this? Because ID is directly proportional to W, right? So when you see the factor, it will directly replicate into your current. So there is a factor of 21 times in width. The difference is 21 times in width. So that same factor will replicate into the currents, right? This is clear? Now we know I1 equal to I3 because they are in series. This is 3, this is 1. So we know I1 equal to I3, this current, which is basically I. And I1 equal to I2. This is also known from these two transistors. So now what happens? Let this be Ix, okay? So I am applying KCL at X node. So applying KCL at X, what it becomes is basically I4 equal to Ix plus I2, right? I4 is equal to Ix plus I2. So this is 21 times of I is equal to Ix plus I. So Ix is actually 20 times of I, right? So this particular current is 20I, okay? Now here again see, here we have Wn and here that same factor replicates. We have same VGS and all other parameters are same. So the same current will replicate at this particular side, and here also we'll have I to be equal to 20I. Is this clear? How we
Yes, ma'am.
got this 20I, is this clear? So here finally this current is actually 20I. This is 20I. Now we have to find out the small I. We have to find the value of this small I. So once we get this I, we can simply multiply it by 20 and we'll get the final answer, right? So how will we find the small I? So here if we look into this carefully, into this particular circuit, so the current flowing through this particular part of the circuit is I, है ना? I. So this I we can write so here we can write KVL here, which will be 2.5 is equal to VSD 3 plus I small I r plus VSD 4. Oh, sorry, VSD 1 था ना ये, VDS 1. And we figured it out somewhere, right? Like these two are equal actually. In first question we did this, no? There also we had the similar type of diode configuration, and there we found out, like, first of all this VSD will become, D will change to G because D and G are shorted. Then we also know since same current will flow and everything has already been matched, so this VSG is equal to VGS. So it simply becomes 2 times of VGS plus small I r. Now writing this VGS in terms of I and solving it for I, we'll get this I, value of I, and then we have to simply make it 20 times. So capital I is actually 20 times of small I. Got it? Is there any doubt? Okay, I'll go step by step. Okay, please let me know. First of all, how many of you got this Ix being 20I? Is this clear? Have you got this Ix to be 20I? Is this clear to everyone? Does anyone has any doubts? Yes, anyone has any doubt? So could you understand what we were doing till now? Hello?
Yes, ma'am.
Yes, ma'am.
Is this clear how we reached till 20I?
Yes.
Everyone is clear, right?
Yes.
Okay, so this circuit is basically current multiplier circuit. So your reference current was the small I and your output current is 20 times of that small I. So it's a current multiplier circuit. Okay. And how can we find out the small I? Is this clear? This was the second part. So how to find this small reference current I? Is this clear to everyone? Hello? Okay.
Yes, ma'am. Applying
Yes.
KVL to left side.
Yeah. So basically we applied KVL from VDD to mu and we'll solve it. So the final answer that you'll get is 2.558. Okay, so this is what you'll get as your final answer. You can solve and check. Okay, so moving on to the next question. So this is also in similar pattern. See, A is 1 times, B is 4 times, C is 3 times, and D is 1 time. Okay, so here, see here also, the moment you see this type of configuration, you should simply assume that if this current is I, so this current IA, this is, let's say, IB. So IB will be simply IA into B by A. Is this clear? You should simply apply this formula. Okay? Now, here, so first of all, we'll start from here. Okay? So IB कितना हो जाएगा? It will be IA times B by A मतलब 4 by 1, that is 4IA. Okay? The same current will flow through this circuit, this whole circuit, that is from B and C transistor. The same current will flow. So now IC will also be equal to IB, which will be 4 times of IA or 4 times of IREF. Okay. Now here again we see this type of configuration. So यहाँ पे when you apply for I copy, here it will be IC into 1 by 3, right? This is ID. Is this clear? Why same formula we applied again? Okay. So I copy becomes IC into 1 by 3, that is 4 IREF by 3. So it is I copy is 4 by 3. IREF ka value has already been given, 553 micro. 553 microamps. So the moment you'll solve, you'll get it as 737.33. Is this clear? Is this clear? So first of all, this part, is this clear to everyone? Hello?
Yes, ma'am.
Is this clear to everyone? This is clear, no? So this is what we were doing earlier also, right? So there we were going through using the formulas and everything. We were analyzing each and every factor. Then we came across this. So finally also there we got this thing, right? Jahan pe we saw कि like WP was say 21 times of WP, WP dash was 21 times of WP. There ultimately we got our ID dash becomes 21 times of ID, right? Or if you see it carefully, it's actually this expression, the one which we wrote in this particular question. So we used to do the same thing only. Here we have just made converted it into a formula. That is the only difference. So this is clear, no? So hope this is clear. Now moving on to another. So this is also same type of question. So you people can solve it. Okay. I'll go to another pattern, so which is a bit different from this particular thing. So this is same as earlier one. Here there is a little difference. You can solve it and check it yourself. Now moving on to this last question. Okay, so in this particular question, what you have to do, you have to find I out by V in. Okay, and here what is new in this particular question? You have this op amp. So can you quickly let me know what is the property of an op amp? Let's say this is an ideal op amp. So it's already given that op amp is ideal. So what is the best quality that we can pick out of an ideal op amp?
Infinite gain.
Sorry.
Infinite.
Infinite gains.
Virtual ground.
Yeah, virtual ground concept. Or virtual short concept. Virtual ground नहीं होता है. It's actually virtual short concept. So which basically means that the gain of op amp is so high that its different voltage is almost equal to 0. That means the voltage at both the terminals of an op amp will be almost equal. So since here we already have ground at one terminal, so other terminal will also see a ground equivalent voltage. So a voltage which is very close to ground. Is this clear? Acha, second thing what we see in an op amp. So let's say a current I is flowing in this circuit. So what is the advantage that we get from an ideal op amp? Somebody say
Won't draw any current.
yeah, it
Zero
is. So
current.
there is no current, ingoing current, like, so due to infinite input impedance, the current going to an op amp is 0. So basically there won't be any current in this direction. So this current I will simply pass on in this direction. Is this clear? Is this clear? So now
Yes.
since this op amp is not drawing any current, so whole of this current will go through this feedback path, and this comes across this MOSFET as I. Okay. Now again see here, okay, since nothing has been mentioned, like there is no factor which has been mentioned between these two MOSFETs, that means these two MOSFETs are actually matched. And when these two MOSFETs are matched and they have their gate shorted, that means the same current will flow through these two transistors. So this is simply a current mirror circuit, right? This is how a current mirror circuit works, no? Is this clear to anyone? Everyone? So this circuit basically looks like this. So this is how this circuit looks like. Here, since it is not grounded, so I will not ground. But this is how it looks like.
But it's not current mirror, right?
But here, if let's say here you are getting current as I, okay, I current is flowing, and there is some bias voltage V over here. The same bias voltage is getting applied to this particular MOSFET. I mean, okay, so since there is no diode configuration, you are saying like this is not a current mirror. But see, that's what I said. ID only, so in saturation, ID sat is only a function of VGS, right? So the moment you have VGS equal and physical parameters like Wn and Ln equal, then you'll see same current, no? Does this make sense? This
Yes, ma'am.
particular discussion, this makes sense, no? I understand why
Yes.
you are saying it's not a current mirror. That's because you don't see this configuration, the diode connection, the short between drain and gate. I understand, but here also you see in this particular circuit, you have some current coming into your this particular MOSFET, okay, and you have same like bias applied in both the like in both your MOSFETs, okay, and there is no other factors which have been mentioned, so it is safe to assume that both the transistors are matched, right? So if both the transistors have same equal W and Ln and equal VGS, then they will see same currents, no? And how to find out that current? So it is safe to say like I is equal to I out. Is there any
Yes, ma'am.
confusion?
Yes. But ma'am, I have a doubt. But
Hmm.
can we draw same conclusion for BJT also? When we
Uh,
connect the both base towards the base,
when
will there be an issue for BJT?
okay, so if there is a BJT and we are saying if no, so here so this is what you're trying to say, no? Like if this is let's say a connection,
Yes.
and is it safe to say that if these two are connected, then is there a possibility that the current flowing through this will be equal to this? Mm, sometimes actually yes, but will it be the case always is the question. So the
Okay,
advantage
ma'am.
that we get in case of MOSFET is that there is no gate current, right? So it doesn't affect. But in case of BJT, we have this bias current IB, and it changes the biasing completely. No, the moment there is a small imbalance in IBs, so let's say one sees different IB than others, then there is a issue. यहाँ पे since there is complete isolation, so it's safe to say कि we are not seeing the effect in case of a MOSFET. But BJT, I feel there will be some, so it won't be very safe to say always कि if this type of connection is there, then we will not see any, like there will be same current flowing. But in case of MOSFET, it is safe to say. The reason being, first of all, there is, okay, yeah, so first of all, the reason being that there is no current in gate. So gates are completely isolated. And secondly, our saturation current is actually a function of VGS, right? So if they both the transistors are completely matched with the Wn and Ln being same, and they have also mu and Cox same, at that point of time, if their VGS also matches, then and VTs are also same. So the moment we say a transistor is matched means all these factors are equal. the only thing that remains is VGS. So if this VGS also matches, that means all the factors coming into your current, saturation current, are equal. So your currents will be same in case of MOSFET. So there, yeah, it is safe to say that this current will be equal in case of MOSFETs. But for BJTs, I have to check it once. I don't want to pass a wrong statement, so I'll check it and let you know maybe. But in MOSFETs, yes, we can say, because we can see clearly, you know, like all the factors being satisfied. So, yeah.
Yes.
And here, so since nothing else was given to us, so very minimal information is given. Only the resistance value is given to us, and we have to find this output current. And we can clearly see, like at every point, our explanations are valid. So we can go ahead with this method. And this I will be basically Vn by R, no? So we want I out by Vn. This will be basically 1 by R. So this is what is asked. So what is the value of I out by Vn? So we'll finally get 1 by R. So, yeah, we can go ahead and solve it in this one. And the answer that we'll get is 62.11. Yeah, this is the answer that we'll get. Is this clear?
Yes, ma'am.
Okay.
Hello.
Yes.
Ma'am, in question number 9, is there any correction?
Question number 9.
Ma'am, can you please open the question number 9?
Question number 9. I have to check. If you feel like there needs to be some sort of correction, maybe you can raise it in forum. That will be helpful.